This is one of the driest places on Earth. Sometimes it feels like being on the moon or Mars.
During the day is a fantastic place, but during the night is absolutely astonishing.
So hi everybody, welcome to this year Women of CTA event, an event that we use to celebrate the International Day of Women and Girls in Science. This is the fourth edition, already 4 years, in which we met amazing female astrophysicists and engineers. And this year, I'm extremely happy because we have wonderful speakers talking about very different fields. We are going to hear them talking about science education, cosmic rays, the mysterious dark matter. But before meeting them, let me just remind you that after all the presentations, we are going to have a dedicated question and answer session. So don't be shy, send your comments, your questions. At the end, we are going to gather them and the speakers are going to answer them. You can actually start now. You can send your questions during the entire event. Say hi to us now. Let us know actually where you're connecting from. We want to know that you are there. Okay, and in the meanwhile, let me already invite our speakers to join me here in the screen. Our women of CTA of this year, we have Wolter, Heide Costantini, and Judit Pérez. Hi, how are you guys?
Hi.
Okay, so well, first of all, let me thank you for joining us today in this event. We are going to have actually a very short presentation explaining why we are doing this event before jumping into your presentations. But I wanted to say hi, and also I'm going to make you the same question as to the audience. Where are you connecting from? So Anna, for example, let's start with you. Where are you now?
I'm in my office. Well, not really my office. This is a room of the Osservatorio Astronomico di Brera. I'm just above the botanical garden and happy to be with all of you.
Happy to have you here. The environment actually looks very nice, a library or something like that, right?
Yes.
I love it.
A small room with a lot of old books.
So welcome to the event. So Heide, where are you now?
Yeah, I am in my office in the Centre de Physique des Particules of Marseille in the south of France.
Nice, I love it. We are going to see that actually we are in different countries. Judith, where are you actually?
Hi everyone. So I'm indeed also in my office with my two office mates indeed, but they are here listening to me. I'm in the IFT in the campus of the Universidad Autónoma in Madrid in Spain.
Great. So again, thanks a lot to the three of you for joining us today. I'm going to start with this short introduction, and then we are going to move to your presentation. Really looking forward to hearing your talks. Okay, so let's start. I'm going to share my slides now. I'm going to briefly introduce why we are actually doing this event. So as I mentioned at the beginning, we are doing the Women of CTA event because it is the International Day of Women and Girls in Science. But what question would be why we are celebrating this day? And the reason is that unfortunately, right now, we are still having gender inequity in the field. So in 2015, the United Nations decided to fix this day, February 11th, to raise awareness about this gender inequity and also highlight the work that the female scientists were doing in the development of science. So let's have a look to the current context. If we take into account all the scientific fields, we see that so far only 30% of researchers worldwide are women. This is not the same in all countries. Actually, if we have a look to this map, we can see that some countries already reach what we call the gender parity in terms of percentage of women and men as researchers. Some countries in Central Asia or the Latin America countries. Another ones, unfortunately, are well behind in the south of Asia. For example, we can see that actually some countries do not reach the 20%. No? But in overall, from the countries from which we have data from around 150, 30% of them have reached this gender parity, as I said, in terms of percentage of women and men as researchers. Nevertheless, even these countries have to deal with some issues. They have to deal also with the vertical segregation and with the horizontal segregation. The vertical segregation is when not all genders have the same opportunities when moving forward in a career. And actually, that is what happens to women in science. As you can see here in this plot, we are losing women in each step of the career, from when they started in the university, moving through the master, the PhD, and as researcher. This phenomenon is what we know as the leaky pipeline. It's a metaphor. In the same way, a pipeline that is broken is losing water in each gap, we are losing women in each step of the scientific career. And then we have to deal also with another phenomenon, the glass ceiling. We do not only have fewer women at the highest stages of the scientific career, but these women also have more problems to reach the decision-making position, the highest management positions. In fact, in 2015, only 50% of the universities in the European Union were led by women. And if we have a look to the Nobel Prizes, so far, only 25 women have been awarded with this prize in a scientific field. Of course, things have been improving in these past years, but yet this barely represents 3.5%. On the other hand, we have this horizontal segregation. This happens when a field is dominated by one of the genders. And in the case of science, and particularly in the more technical careers like engineer, mathematics, or physics, these fields are dominated by men. As you can see here, only 30% of the female students decided to follow these technical careers. And this is a problem. This is a problem, especially, as I said, for the technical fields like physics, and of course the related fields like astrophysics, because we do not only have to deal with the fact that fewer women are deciding to follow these careers, but actually we have to deal with the aforementioned leaky pipeline. So at the end, we do not only have fewer women coming to our careers, but also we are losing them as they move in the scientific career. Well, so as you can see, things are improving in these past years, but there is still a lot of work ahead of us. We need to break with gender stereotypes that are one of the main causes that prevents women to select a technical career, prevents also women to reach these decision-making positions. And also we need to work to highlight the work done by the women in science, trying to show that they are strong female role models in the field that can inspire the next generations. And this is the reason why we are doing the Women of CTA every year. It's our small contribution in this international effort during the International Day of Women and Girls in Science. And as I said here, our goal is to celebrate it now, to put an end to this gender inequity and help promoting the women behind the science, with the hope that in the future we don't have to celebrate it anymore. And with this, I finish, and I would like to invite our speakers, our first speakers, the main player of Women of CTA, which it is Anna Wolter. Hi, Anna, how are you?
Hi, it's very nice to be here and to be talking with these great women that will be present today.
We are very happy to have you. So before starting your presentation, let me introduce you for the people that maybe don't know who you are. So Anna is a researcher, as she said before, from INAF at the Osservatorio Astronomico di Brera in Italy. She has been always worked in the high energy astrophysics field, particularly studying the extragalactic universe, also studying them from a multi-wavelength approach. Well, Anna has been very involved always in outreach and education programs worldwide. She has delivered more than 200 conferences for schools and public lectures. And among the different positions she has, she's the country representative of Italy in the CTA Outreach Committee, an international network for the communication of CTA. She also makes part of the editorial staff of the Edu INAF, the outreach magazine of INAF, and of the Astro Edu Italy, so the Italian version of the IU portal of peer-review astronomy education activities. So again, thanks a lot, Anna, for joining today and share your knowledge, and whenever you want.
Thank you. So I will talk a little bit about myself and my work as both an astronomer and an outreach person. And when I wanted to tell about myself, I looked it up, my name in the net, and this is what I found. Are different ways in which I am present in internet, and it gives you a little bit of what I've been doing in these years. And this is already been told by Alba, and I just want to focus a little bit on my research. And this is a galaxy that I've been studying for a lot of time, but perhaps more to the point, since we are talking about CTA, is that I've been studying also objects with jets, like blazars, BLACs, and radio-emitting AGNs, of which we can see here an example, that these jets are pointing towards us, and they represent one of the more energetic sources that we can study in the universe. So what does an astronomer do? What is in the mind of everyone is that we look at the sky, and this has been true for most of the time until 1600. We were looking with our eyes. Then the telescope came, and many women were looking with the telescope. And now we have many more complicated instruments. Like, for example, we see the radio telescope, with which Jocelyn Bell Burnell was discovering pulsars, or little green men, as they were dubbed jokingly at the beginning. I've been recently in a press conference to announce that Milano will have the first statue dedicated to a female scientist in all Italy. There are no statues of female scientists of any kind in Italy, and Milano just had recently the first statue of a woman, which is a specific woman and not just a random idealization of a saint or something of this kind. It's been a very interesting work to be part of that, and I can just show you the rendering of where the chosen statue will be put. And it's very nice that this will be just in front of one of the first and major university in Milano, Università Statale, so that all the young students, both women and men, will see this and will have the opportunity to think about that. And this is me. This is one of a picture that a photographer, a friend of mine, took me of my office a few years ago. I look much younger then, so a bit of envy for that times. And this is to show that we are not really looking at the sky anymore. We are looking at the computer. This is quite an old computer. I have a different one now. And we look and we print a lot of paper. I remember when we said that computers will make away with papers. We will not have any paper anymore. And this is definitely not true. So we have papers to read and to write, and colleagues to work with, to interact and discuss. What do we use now to make research? And I just show a few of the instruments. We go from radio telescopes that use the light that has the longest wavelength and made images like this one. This was recently created by using the newest radio telescope, the first part of the SKA, the Square Kilometer Array. And this is our galactic center. This is an amazing image. There is a lot of information, but I think also it's a very nice image. You could frame it and put it on your wall, even if you don't know what it is. And then we use both from instruments from ground and from space. And for instance, you can go to the infrared when you see the heat that sources emit, in a sense. Infrared really, it's heat for our temperature, but for the universe, it's still very cold. And this is a nebula of where new stars are born from the interstellar matter. And we have optical telescope. We have telescope from the ground and from the space. This is the Hubble Space Telescope. Just recently, the James Webb has arrived in his observing place and is starting to collect light. And we look forward to see what we will have new discoveries from this very large and nice instrument. And with the telescope, we can make very nice images, and some of them are very known to most of the public. It's the easiest way, the easiest band to study, because our eyes are sensitive to this. And so we are more used to the optical vision of the universe. But then we go to the higher energy and we use X-ray and gamma ray visions. And most of these instruments are above the atmosphere, because the atmosphere absorbs all this light. And this is good because if not, we will not be able to live on the surface of the Earth, because these are very dangerous radiation that can disrupt the DNA molecules, for instance, and will not allow the life as we know it to exist on this planet. And with X-ray images, we can look at a lot of different things. And of course, we don't see X-ray light, so we use usually false colors that we can use, for instance, to describe this is a supernova remnant. Different colors describe both the motion of this emitting, this light-emitting particles and produced by the explosion of the supernova, and also the different elements that are produced and dispersed in the space around the star when the star explodes. And no, this is not a coronavirus, but it looks a lot like it. And in the gamma ray, we see the hottest universe and the higher energy universe. And again, we use most of the time telescopes that are outside our atmosphere. And we can see here the galactic plane as observed by the Fermi satellite. You see that our galaxy is very bright, but there are a lot of red points all over it. And these are extragalactic sources, which are the ones that I usually study. And then we go to the Cherenkov telescope. The Cherenkov telescope are a step forward in the sense that we go to even higher energies. And it's not easy to observe them even from space, because you need to have very heavy instruments, and to make them heavier, it's complicated, and you cannot put them in orbit around the Earth. So we have found a different way of looking at that. And these are, in a sense, optical telescopes that look at a very special light, the Cherenkov light, that is actually produced by a large detector, which is the atmosphere of the Earth. And you can see here again what we're going to observe. One of the best thing is our galaxy, and you can see here this is the plane of the galaxy, and every bright orange and red spot that you can see here is a cosmic accelerator, and it sends towards us both light and particles. And so we have to observe them with Cherenkov telescopes. And to explain these things to the public involves a lot of challenges. And I just take a couple of them as an example of how you can explain things to a public that is not knowledgeable about these things. So what is the Cherenkov effect? It's a very complicated thing because it's when the particles move faster than the light. And this is not easy to explain. We know that the speed of light is the maximum velocity that it can be reached. But this is true for the light in the vacuum. If the light moves in a different medium, like air or water, for instance, it goes slower, not much slower, but enough that a particle that is created with a very large energy and a very large speed can enter the medium at a velocity that is larger than the speed of light in that medium. And in that moment, it makes this bluish light that you can see in a nuclear reactor, for instance, and it's the light that lags behind the particles. How can you explain that? You can explain it, for instance, with an analogy with the sonic bang. Most of us have seen a jet that goes over the wall of the speed of the sound and makes a bang. And what happens that when a particle, a source of light or sound, it's steady, it makes concentric waves. When you start making the source move, the emission of the light is concentric to the new position, and so all the emission moves and gets together until all the new emission and the old emission are summed up in the same point. And when the jet goes faster than this light, then it happens the bang. The jet is moving faster than the sound reaches us. And so if you look where you hear the sound coming from, you don't see the jet, you have to look forward. And this is the same thing that happens to the light. The particle that emits the light is faster than the light reaching us. Of course, at much higher velocities than we with the sound. And we try to explain this. The outreach part involves many different things, and I just summarized a few of them. Very recently, we have been in Genova at the Festival della Scienza, in which we have presented the lab to show to people how these things work, how the atmosphere can be an instrument to see this particle of light, this blue very flashes that comes towards us. And this is and then we had a conference to explain this Hawk radiation, this gamma ray that makes it's very powerful. And we've made a few movies of the place in which we were having the lab, and this is our Federico, who was running the lab, that was being interviewed, and this is the Italian Astri, which is a precursor of CTA. And then also Martina was going to see, and these are the kids at work on this realization, and they were very happy of making their own shower of particles and lighting it up. And then we had another festival in which there was a connection with Tenerife, where in the Canary Island, where the Astri mini array is being built. And it was very nice. I learned that there is this plant, retaba, that is protected by the park, and to make the holes that you can see they're digging very large holes to put the basement of the telescope, you have to either move the plants, if you can do that, or if not, you have to plant new ones so that the total number stays the same, because they are protected. And this is a very nice things that we can learn and suggest also to other people. And this will be the position of the Astra telescope in Tenerife. And to do that, we prepared also some material to explain how the Cherenkov light works and what we are doing for that. We have also some social channels. And the only thing that I want to share is just small numbers. So I don't know if this will stay if we get larger, but I suggest also others to check about this. Most of the social and in general all the social channels are followed mainly by men and not by women. But if you look at the people reached, the people that have seen the things, maybe not interacted, this is about 50-50 in our case. So it is possible that maybe women are less likely to interact, but they are reached by your message. So we should think about this and use maybe a different way of communication. I cannot not mention the presence at the Expo Dubai, in which our Alba was the presenter, and organizing this has been, even if I was not there, has been a very interesting situation. And then since Simone is in the background, now I wanted to show this anyway, but he organized a show of pictures, very nice photographs of and also of the Cherenkov telescopes that were shown in very different places. And then we have other things like proposal for kids and other things that we will do in the future. I don't want to keep you for too long. I'll try to explain what we do for showing things to the public. And I want to just conclude with this example. This is a detection of the crab with the Cherenkov telescope, and you can see that on the left you have a graph explaining this, which is really not easy to explain for someone that is not in the field. While on the right you have an image of the crab, the source that makes this signal, adding the optical and the X-ray image of this source. So it's a lot easier to explain things if you have images, but we should learn how to pass the message even by using these graphs. And I conclude with this Albert Einstein saying that everything should be made as simple as possible, but not simpler. This is one of the mantra that we try to always abide, to try to use the good words to explain things to everyone, but not banalize the message, because we are talking about the universe, the house in which we live. And so this is always important, and we want to share this with you. So thank you very much for listening. And if you have any questions, I'm available.
Thanks a lot, Anna, for this very nice presentation. Amazing, very interesting, the science communication activities that you carry out. So we're going to move now to Heide, but let me remind all the audience that if you have any question for Anna, as she said, now you can leave it already in the chats in Facebook and YouTube, and at the end, she will answer all your questions and doubts. So thanks again, Anna. We are moving now to Heide Costantini. Hi, Heide.
Hi.
How are you?
I'm
So,
fine.
as we did for Anna, let me introduce you to our audience. So, Heide started as a nuclear astrophysicist, actually, at the underground laboratory of Lanzaso in Italy. And during her career, she worked at different institutes worldwide, including INAF in Italy and the University of Notre Dame in US, where she actually started to get interested in the high energy sky. In 2010, she became assistant professor at the Aix-Marseille University in France, where she is right now, and she joined the Cherenkov Telescope Array Consortium, where she currently serves as the Galactic Working Group co-coordinator. And there, besides working on simulations for the small size and medium size telescopes, she focuses on the observations of the so-called pevatrons, one of the most powerful sources in the universe that I'm sure you're going to talk about. So whenever you want, Heide.
Okay, thank you very much, Alba, for a nice introduction. So, okay, so let's see great, thanks. Okay, so I will talk about the pevatrons and in particular the origin of the galactic cosmic rays. So first of all, what are cosmic rays? So cosmic rays are charged particles, mainly protons, that continuously bombard the Earth atmosphere. And actually, they are known now since more than a century. They were actually discovered by Victor Hess, that was an Austrian physicist, who in 1912 did a balloon flight. So here you see a picture of Victor Hess doing when he started one of this journey. And he went up until 5,000 meters. And what he saw was that he was actually measuring the radioactivity, the environmental radioactivity. And what he saw that at some point, the radioactivity was increasing by going higher in the atmosphere. And this was not expected if the radioactivity was only coming from the ground. So this somehow was an evidence on the fact that there was something, so what he called then was called cosmic rays, that was actually ionizing the atmosphere. So this was really the first, let's say, evidence, or better, the real discovery of these cosmic rays. And actually for that, he was awarded with a Nobel Prize in 1936. So what do we now know after more than a century about the cosmic rays? So this is one of the most famous plots in modern astrophysics, and I promise it's one of the only plots I will show. And what does it show? It's actually the flux, so the number of cosmic rays per square per area as a function of their energy. So what can we see here is that there are two very striking things. One thing is how fast this cosmic ray spectrum decreases. This is practically a pure power law with a change actually in slope in this region here. And the other thing is the energy range. So the energy range increases of several orders of magnitude. So what we know now from this spectrum is that in the lower energy part, so here, and we were somehow below this kind of change in the slope, what is thought now is that the origin of these cosmic rays is mainly galactic, while if you go to very, very high energy, the origin is now to be extragalactic. So this region here that is known as the knee, due to this change in the slope, occurs at the order of 10 to the 15 electron volts. So now the problem is, do we know where and what these cosmic ray sources are? So the name that has been given to these sources is pevatrons. So it's similar to cyclotron, so since it's a machine somehow, it's a natural accelerator that is able to accelerate this charge particle until the order of the PeV energies. So what do we know about these pevatrons? So from, let's say, theoretical calculation, we have some hints of what a pevatron could be. So one of the best candidates is a supernova remnant. So this is a picture similar to what has been shown by Anna before. So this is a supernova remnant. That means this is what happens after a supernova explodes. So after a massive star explodes at the end of its life, it emits this material, and there are these shock waves that are very fast. There is a lot of material, magnetic fields, and what happens? This is the ideal place to accelerate charged particles. But in fact, even if these are seen to be very, very promising, there are hints that maybe these are not the only, let's say, the only contributors to the flux of cosmic rays. There are other actually possible regions where cosmic rays could be accelerated. For example, these star-forming regions. So these are regions that are very dense and in which you have actually very strong winds coming from massive stars. And again, due to this very extreme environment, you could have extreme acceleration, so producing cosmic rays. But this is somehow coming also from some theoretical calculation and from theoretical prediction. But what we would really like to do is actually to detect these pevatrons. So ideally, what we would do is that since cosmic rays are mainly protons, we should just go back and look where the protons are coming from. But one of the problems of protons is that these are charged particles. So from the journey from the source to the Earth, they are deviated due to magnetic fields that are present in the galaxy. So one nice feature is that when these protons are accelerated in the source, there is a probability that these protons are interacting with the surrounding material and produce neutron particles, like photons, very high energy photons, so gammas, and neutrinos, these very elusive particles that practically interact with anything, with nothing. But the nice thing is that they are neutral, so they can come straight from the source. So if you go back and look where these gamma rays are produced, we could have actually a chance to see these pevatrons. Of course, they have to be some characteristics. They have to be very high energy, and that's what we are looking for with gamma rays. So do we have already some hints about pevatrons in our galaxy? So already something like 5 years ago, there was actually some first indication of a candidate of a pevatron that was actually done with the Hess-Cherenkov telescope. So you have seen this figured already before by Anna, and this is actually how we would see somehow our galactic, the Milky Way, if we would see gamma rays directly. So this is the plane of our galactic, of our galaxy. So if we look in the direction of the center of the galaxy, where we know that there is a supermassive black hole, the region around these supermassive black holes has revealed extremely high energy photons. So this was the first hint that pevatron, that this region here could be a pevatron. But still, the energy density that is coming from these gamma rays could not explain completely the bulk of the flux of cosmic rays that we actually detect on Earth. So what is extremely interesting is, especially, so it's really a very, very exciting period, is that last year there was a big discovery. So for the first time, 12 pevatron candidates were detected by a gamma telescope that is called LASSO. So LASSO is a gamma telescope that is in China, and it detects gamma rays by looking directly at the product of the electromagnetic showers in the atmosphere. So what he detected for the first time have been extremely high energy gamma rays. He arrived until seeing gamma rays of the order of the PeV, so really at extremely high. But then one would say, okay, it's done. LASSO have found the pevatrons, but this it's not completely true, because one of the things is that we not only need to see very high energy gamma rays or ultra high energy gamma rays, but we also have to identify the source that have created them. And until now, just one source has been actually firmly identified, that is the Crab Nebula, but the other one has still to be identified. Moreover, we have really to understand if these gamma rays were really produced by cosmic rays, or they could also be produced by, for example, electrons. So there is still work to do to understand what these pevatrons are. And of course, last year has been really exciting, because for the first time, extremely ultra high energetic gamma rays has been measured. So there is really a hope that we are actually close to understand the mystery of the origin of galactic cosmic rays. So what is the future? And also the present. So what we need would, of course, be to try to put data together and try to understand and to this problem. So we have talked about already last, but of course there is CTA. So CTA will be able to look also at very high energies, but especially it will be able to see the details of the sources. So this will be extremely important, having LASO detecting the sources and CTA detecting them, and then looking at the details, thanks to the wonderful characteristics of CTA. And then another thing that really would be very, very interesting would be to couple this with neutrino detectors. So neutrinos are also produced by cosmic rays, and detecting both gamma and neutrinos would be extremely useful to really identify the pevatrons in our galaxy. Okay, so I hope with that I showed you a bit what is the challenge and why it is actually really exciting for looking at pevatrons with CTA. And then now I want a bit to show you a little bit how I arrived actually to study pevatrons with CTA. So my career a little bit is actually related to the evolution of a star. I actually started during my master's thesis and PhD, and also first postdoc, to study nuclear reactions that were occurring in stars, and especially in the very quiescent phases of stars, so for example, hydrogen burning in the sun. So the energy that we're exploring with these cross-section measurements was of the order of keV. So you see orders of magnitude lower than what I'm looking now at PeV or TeV. And also, I was working in a collaboration of around 30 people. So I started quite small, I would say. Then, becoming a permanent researcher, I got interested in more the high energy sky, and I joined the Antares neutrino experiment. In that, actually, I was especially interested in studying the possibility of detecting neutrinos coming from a supernova explosion. So again, I increased a bit the energy, MeV, and also the size of the collaboration. So Antares is around 200 people. And then in the last 5 to 10 years, I joined CTA, and here really I started to study objects of extremely high energy, and also the number of people actually increased quite a lot. So CTA is a huge consortium with around 1,500 people. So this shows a bit somehow the evolution, but it's really interesting because this brought me to have actually different kind of experiments, and also the way of doing research in different sizes of collaboration. And just also to show a little bit, also the environment is quite different. So when I was working at an underground laboratory, I worked at the Gran Sasso National Laboratory in Italy, close to Rome. This is actually a wonderful place with very nice mountains. And the everyday life, I was actually working directly in the tunnel. So this is the container where we had our very, very small accelerator, where we were reproducing nuclear reaction occurring in the stars, in particular in the sun. And the work was also actually quite experimentally. So we were actually setting up the target chamber, the detectors, the electronics. And this was actually really nice. It was a very small collaboration, and you were doing actually quite a lot of hardware. Then when I went to Antares, things changes. I went to the sea, and there the difference is, so the Antares is an underwater detector, a neutrino detector that is actually quite close here to Marseille. And the shifts changed quite a bit, because instead of the tunnel, now we were doing shifts in this very nice villa here. And but we had also the occasion to do sea campaigns where we had, for example, to deploy or to recover some lines. So this is taken from one of these sea campaigns. And of course, the other things is the shifts are quite different. So you are actually mainly looking at some screens and doing calibrations and looking if your detector is actually behaving as it should. And then finally, I arrived to CTA. So CTA, of course, it's not complete yet, but there are a lot of prototypes that has been built, and it has been really a pleasure to participate to some of test campaigns of this prototype. So This was a test campaign that was done in Adlershof, close to Berlin in Germany. And also we did test campaigns of one of the small-sized telescope in Paris, at the Observatoire de Paris. And this has been really a pleasure, of course, to work in this, but you could not really do real measurements, or better, you did some calibration and so on. But of course, if you look at the sky here and here, it's not ideal, for doing for looking at sources and measuring the sky. But now we have one first telescope on site, that is the LST one. And I'm really looking forward to have my first shift that will be in 2 months from now at La Palma at the LST-1 telescope. Okay, so thank you very much.
Thanks a lot, Heide. It looks like a very exciting field ahead of us with the Pevatrons, and once CTO is ready. So thanks a lot for this presentation. And again, to the audience, if you have questions for Heide, she will answer them all at the end in our question and answer session. So let's go with our last speaker of today's event, Judit Pérez from Spain. Hi, Judit.
Hi, everyone.
How are you? So let me introduce you to the audience too. So Judit is a last year PhD candidate in the Instituto de Física Teórica in Madrid, in Spain. She graduated in physics in Universidad de Valencia and moved to this institute for her master degree, where she joined the Dark Matter, Astroparticles and Cosmology group and started the PhD focus in this gamma ray search of dark matter. Judit is actually a member of the Fermilab collaboration and also of the Cherenkov Telescope Array Consortium, where she serves actually as coordinator of the Galaxy Cluster Task Force and coordinator of the Dark Matter Tool Task Force in the development of software for the analysis of dark matter sources. And also she is currently, and very recently, the country representative for Spain in this CTA Outreach Committee. So thanks a lot, Judit, for joining us today. And whenever you want, the floor is yours.
Thank you very much, Alba, for the presentation. I have to say that I'm very, very glad to be here with all of you very wonderful and bright women. And what I'm going to talk to you today is a bit of the work that I've been doing and the path that I've been going around since I started my PhD here in the IFT already 4 years ago. So we are going through a journey to trying to disentangle this dark universe, these things that are here, but in principle, we are not able to see. So before we start, let's talk a bit about the things that we know that there are in the universe. These celestial objects that from our bare eye, we are able to see in the starry night when we look up to the sky. For example, we know the existence of stars. We really well know our star in the solar system, which is the sun. Then we also know there are other planets outside from the Earth where we live that are, for example, the rest of the planets of our solar system. But there are other planets, indeed, which are outside our galaxy, other what we call usually exoplanets. And what happens, what we see, is that these stars and these planetary systems usually gather together in what we call the galaxies. Indeed, our planetary system is sitting in one of the spiral arms of the Milky Way galaxy. We know this, we have observed this, indeed, in a very, in a very dark night, we are able indeed to see a bunch of stars that are in the Milky Way. So, okay, let's gather all of it together. If we count all the matter that we know that exists from the Earth, from outside the Earth, in these stars, in these planets, on the galaxies, all the dust that is surrounding us, all the hot gas that, for example, goes out from these supernova remnant explosions that Anna and Heide were talking before, we only can amount up to the 5% of the matter content of the universe, of the energy content of the universe. The rest is in form of something that we cannot directly see, which we usually call the dark matter and the dark energy. This amounts up to the 95% left of the energy content of the universe. And one will naively ask, how can this be possible? I mean, we've been observing the sky since before the ancient Greeks. So how can we miss so much of how the universe is made? So, okay, let's take a breath and let's see what are the things that have changed since we started seeing and looking to the sky. We know that we have observed the sky, as Anna was presenting before, with our bare eyes. And with our bare eyes, we are able to see some light of the universe, which has some kind of energy, okay? With our eyes acted as a detector. From these detectors, we are able to build the first telescopes. Here I'm showing, for example, one of the first ones that was built, a reproduction indeed, the one that I'm showing is a Galileo telescope. And then we added like this new instrumentation to our receptors, which are the telescopes that we all can buy, for example, in some shops. But then we have moved on a lot since then, right? As Anna was also talking, and also in the last slides of Heide, today when we are trying to look for the things that are in the universe, we look at computers because the receptors are not longer our eyes, are the receptors that we have built, these very complex and extremely powerful machines that are able to recollect all of these different lights that the universe has to offer and put in words that us can understand. There are different lights that we can receive from the universe, but for example, one of the recent ones, of course, are the gamma rays. And this is because these are the most energetic light that we can get from our universe. Here I'm showing a picture of the Fermi-Lab telescope that Anna has also showed before. It's a satellite telescope and has been taking data since 12 years ago. And of course, the future of the field that will help us to unveil all the different, the nature of the dark matter that will be the Cherenkov telescope array, which, as Heide has already said, we have already our first telescope in La Palma. So, okay, we know we have different instruments, so we are more capable. What have we learned since these very first telescopes to the ones that we have today? Okay, when we are looking from our bare eyes to the sky, we can see some stars, we can see the constellation and draw these very first maps. Indeed, we still can compute some orbits of the planets that are around us, like we used to do. But now the photos, like pictures that we have of the universe, are very different and can look very different depending on the energy of the light that we get. For example, here I show you in the upper light pictures the picture that we can get using the Fermi-Lab telescope. This is the picture of gamma ray sky, the highest energy that we can look for up to we get to CTA. And this is this is like our galaxy looks like from the telescope. Okay, here in the middle we have what is called the galactic plane, and in the center the galactic center, where it's hosted a very supermassive black hole. But then we also have the picture that is just under the one that we were talking. This is known to be like the very first picture of the universe. This is the oldest picture of the universe that we are going to get. This picture was taken in the moment of when the universe was still expanding a lot. So all the universe was cooling down very quickly. So at the end, the light that was just going from particles or different, like it was a very hot soup, like we say. And at this moment, the light was able to travel and to reach us. This photo explains us this moment. And from the analysis combined of these two pictures, we are able to obtain a lot of information on how the universe has been formed, of how has been evolved, and how we are going to go. And this is the moment when we jump from observation of the universe to really track and try to disentangle the different mysteries that these different pictures are unraveling. So what we have known and what we have been looking for, the cosmologists and astrophysicists during the last decades, is how are these pictures can be connected in a congruent and in a coherent way, okay? So for this, we are going to look of how the universe has evolved. First, we start with a point, like the universe is all concentrated in a point, and then it expands like in a very big explosion full of energy, and then all the particles are created and start to interact one with another, just not making any sense. Like any kind of system that is bound and is stable can be formed indeed. Then the universe starts to expand, gets bigger, the space and time starts to get bigger and creating this universe. And as this goes through, the universe gets cooler. So the particles every time are having less and less energy, meaning that they are able to form the first atoms and subsequently the first stars, and we are able to start to see them. But then when we look at all this information that comes from this very nice picture that I was showing to you, we arrive to two main conclusions. First is that we do not have enough mass, so the gravity only is able to put this matter that we know all together, forming galaxies, forming stars. This is the first problem that we found. And the second problem that we found is that how the hell the universe is expanding, where it's coming this energy, we don't really know. So for us to understand how the universe has grown until what we can see today, we need to add two dark components. First one, what we will call dark matter, which will be the responsible of the formation of all the structures that we can see in the universe. And then the second one, which is the dark energy, which is the responsible of the expansion of the universe. Indeed, we are going only to focus into one because we don't have time for all, which is dark matter. Since when we do know that dark matter exists, like how many times? Well, indeed, only since the early 1930s, we have the evidence for like this kind of invisible matter component. And this comes from mainly the observations of an astronomer, which is called Vera Rubin. She was observing these galaxies and she was trying to measure the velocity of the rotation of these galaxies. For here, we have the plot that she was seeing and the results that she was obtaining, okay? What we can see in the x-axis, this one, is the distance with respect the center of the galaxy. And then in the y-axis, in this axis in here, we can see the velocity. While one will naively expect from the gravitation that we know from school, this Newtonian gravity, is that the farther you go from the center of the galaxy, the slower you will get, right? That's common sense. Well, indeed, that was not the case. What was she observing is that instead of decreasing the velocity as you moved outside the galaxy, you are getting higher velocities. And this can only be explained, meaning that this matter that we are seeing is not the only one, because the mass that we can measure from the galaxies can be directly obtained from the light that we get. So if this is the mass that we see from the light, there has been something hidden. But still, this is not the only place these weird things were happening. This can also be seen at all different scales in the universe, from galaxies, from the picture that I showed you on this very first picture of the universe, and also at galaxy clusters scales, like the one I'm showing you here, which is the bullet cluster. In blue, we can see like the center, the mass centers indeed of the bullet cluster. This is a cluster that has go through a merge event with other cluster, just like this, okay? And then we can see like the two front shocks in pink, and the mass center of the galaxy cluster in blue. And what we can see is that they do not coincide. I mean, if you see the picture, these pink front shocks are where the standard matter, the matter that we know and we all love, it is. However, the mass center of the galaxy cluster is displaced of all two. So something weird was happening here. And for all of this information from all of the observations that we have gotten since the early 1930s, there are some things that we already know from that matter. We know that it should be electrically neutral. And what this means? Okay, it means that it cannot emit or reflect light, because if not, we will have seen it already. Then we also know that it should, in the best case scenario, very weakly interacting with the rest of the matter, because if not through the light, there are other kind of interactions that can reach us through this through the telescopes. So there are no way they are really talking too much with the rest of the matter that we know. And finally, it should be also collisionless, since, for example, in the bullet cluster picture that I showed you, we can see the front shocks in pink corresponding to the standard matter. However, the rest is like, we do not care about, we have crashed between other galaxy clusters. We are very okay here. They are almost unperturbed. So this is really a challenge to try to detect something that not emits light or reflect light, that really can interact at best very weakly with the rest of the standard matter, and cannot even collide with itself, which it's or not most. So this is very challenging. The only way that we have the proofs of the existence of dark matter, and that's why we know they exist, are the gravitational proofs, like the rotational curves of the galaxies that I just showed. However, physicists and astronomers are wondering which kind of dark matter is able to solve all these problems. Like, we need a dark matter that has mass and is able to pull together all this ordinary matter to form the structures, but it also needs to fulfill all these required conditions. And we have a bunch of different models. It's like a zoo of kind of models for dark matter. We have dark matter, which can be a particle that is, I don't know, 1,000,000 times heavier than an electron, but also 1,000,000,000,000 times lighter than an electron. Then we have other kind of particles that are not interacting in the same way that the others, and also solve other problems that we have already with standard matter. We can have particles, but we can also have very big objects, like not point light, like, for example, primordial black holes. So this is really a zoo. And as long as we do not find exactly which one is the dark matter component, maybe it's not only one, maybe it can be some of them, 2 or 3, we don't know. The thing is, okay, this is really a challenge. We have a bunch of different models, all of them seem very difficult to detect. How do we plan to detect dark matter, really? Okay, so fortunately, this is not the end of the story. There are some models in which the dark matter is still very weakly is able to interact with the ordinary matter, okay? And this is really the key point to detect dark matter. Through these interactions, we are going to be able to detect signatures of annihilation of 2 different dark matter particles, or even the decay of a dark matter particle into a particle that we know, like, for example, electrons or protons or antiprotons, or neutrinos, or, of course, gamma rays. And gamma rays, as already Heide was saying, are really nice to detect new sources, because as they are electrically neutral, they just point back to the origin of their source. So once we receive a gamma ray which is coming from dark matter, we are going to be able to see where this dark matter is from. But okay, for this, we need to know where to look for dark matter, right? So yes, you are totally right. And from the simulations and from this information of the different pictures of the universe, we are able kind of reproduce where the structures are. So that means that the structures that we see, the galaxies that we see, are seated in a halo of dark matter, okay? So where these structures are formed is where we expect dark matter to be denser, to be more dark matter. These places, as I'm showing here, this is a very nice simulation showing the different bright spots of dark matter in our galaxy, for example, the galactic center and also the Milky Way halo. We also have some companion galaxies to our Milky Way, which are usually called dwarf satellites, which are really, really nice to observe. And we also have galaxy clusters. And I'm going to focus on galaxy clusters because I'm a bit selfish and this is what my work has mostly centered. Galaxy clusters are the most massive objects in the universe, are the most massive gravitationally bound objects that exist in the universe. And up to the 80% of their mass is only in form of dark matter. That means that are one of the heaviest objects with accounting with the most dark matter content of the universe. So these are objects that are really, really good targets to focus to look for dark matter. And okay, this is my very, very small contribution to the detection and the unveil of the nature of dark matter. As you can see, we haven't still had the opportunity to detect dark matter, but we have made a lot of progress since then. I've spent 4 years simulating the possible and very kind of different dark matter sources for future CTA observation and also making some predictions of what CTA will be able to make. I tackle the different of knowns of how dark matter is really distributed according to the different targets, if it's in a galaxy cluster, if it's in a dwarf spheroidal, and how this can be built, how we can tackle all these uncertainties and put some good prediction and realistic predictions to what CTA will be able to do. And of course, we always are aiming for a detection, but okay, we just need to see that we've been looking for dark matter for almost 100 years. So what we usually do is to put constraints on this bunch of models that we have and try to discard as most of possible if we do not get a detection. And this is what I do, like in this plot in the right hand, for example, all the models that are yielding upside these lines will be discarded for CTA just in case of no detection. Another thing that I've been able to make, and I'm really, really glad of doing here, in my PhD, is that I've been able to work in 6 different projects, all involving dark matter at different kind of topics, but always dark matter related, making prediction, but also thanks to Fermilab to work with real data. I've been able to participate in more than 20 international conferences and to present my work and of course learn from the work of others despite COVID. I've been offered really to coordinate the working groups within CTA and also to develop a specific software for the matter searches. I'm really glad because this will help all the new people coming to CTA to ease their work and also to be able to produce more science once the data arrives. And of course, I've been able to do a lot of outreach activities in many different ways. I've been able to film some outreach videos for the IFT YouTube channel that you can check on YouTube. I've been able to do seminars like this one that I'm doing today thanks to CTA. I've been able to participate in an outreach book that will come soon, and I'm really, really glad. And this is for encourage you to all the curious girls that are outside, even though they are not in the textbooks. There are plenty of girls that has been and women that are scientists that have been scientists and are going to do science because science is fun. It's an adventure. It's working through a path that no one has ever walked before, and you will be the one discovering this. You are trying to understand better our world. In these lines, from the IFT, we have performed a video from the initiative Geophysics and Comic, which gathers information of different women scientists, women physicists, and tries to give visibility and normalize the place that women and girls should have in science. If you are interested in this, the video just came out today and you can check it on the YouTube channel. And for the future, so dark matter remains still unknown, and someone has to discover it because we know that it's already there. And if you're interested, maybe you can join us and you can be one of the ones discovering dark matter. So thank you very much for your attention and for listening to me.
Thanks a lot, Judith. I agree completely with you. Science is fun, so I encourage also everybody that wants to learn more to delve into this field. Thanks a lot for this very nice presentation about one of the greatest mysteries, dark matter. And I would say your contribution is not small, it's important. So thank you for that. And let's start already with the question and answer session. So I would like to invite also Anna and Heide to join us here. Hi again.
Hi.
So I just want to say to the audience, if you have questions to any of the speakers, you can write them now in the Facebook and YouTube channels, and they will try to answer them, I'm sure, all of your questions. Meanwhile, I would like to start. Actually, I was taking notes from your presentations. I would like to start actually with Anna. You have shown that you're doing a lot of different types of science communication activities. One of them are focused on children. And as I mentioned at the very beginning, it's very important to do these kind of activities that also help us to break these gender stereotypes, no? But sometimes we lower the level to children too much. Maybe we don't see if they can understand something while it's not true. No? So actually, based on your experience, I would like to ask you, what are the best activities we can do with children to bring them to this field, or if you have any tips for this?
I think that, first of all, children are not so, I don't know the words used, they're not so low level as sometimes you can think, and you can make them do things much more complicated and important than what some people think. The best way to interact with children is to make them do something. So construct a piece of information or work with their own hands and be the protagonist, be the person in charge of the experiment. And so this, I think, is the best way of putting them in the spot so that they can do something. And if they do, they will learn better. And maybe after that, after having done something together, you can ask them some question or make them do something different to check if they really learned what you were the message you were trying to convey.
At the end, to learn doing something, no, with a hands-on activity rather than just listening. That's a very nice.
And then also we have seen that also looking at the movies on TV is not something that new children. This was good for older generation possibly. Now they look a lot at TV and their phones and whatever. So it's very difficult to catch their attention. So it's better to be there in person and interact with them.
Well, at the end, it's that, no, each generation has a different way to educate, to learn, no? Yeah. So it's very interesting seeing how things are changing. I have a question here from Cindy. So let me show you here. She said, hello from El Salvador. I am wondering if CTA will have any particle detectors like scintillators or water Cherenkov. Would that be helpful in some way, and why not? So Heide, for example, you were showing different detectors. Maybe you can answer to this. Sorry, we were not listening to you. It was muted now.
Okay, that's okay. Yeah, so yeah, it's a good question, because CTA will not have a particle detector, so it will all be an array of tens of Cherenkov telescopes. And for sure, I mean, having scintillators and water Cherenkov, what you were just suggesting, would be ideal. In fact, LASO, that is, let's say, the detector that I a bit flashed during my presentation, will be a hybrid detector. So it will have scintillators, it will have a Cherenkov, water Cherenkov, and also some atmospheric Cherenkov telescopes. So, but it will be mainly, let's say, particle detectors. So for sure, it will be really nice for CTA to have that. And but who knows? I mean, what we know is that there will be other kind of particle detectors, not only LASO in the northern sky, but also as GBO done in the southern sky. And this will be for sure very interesting to put then the data together. So CTA will not do that, but will have partners, and this will be very, very important, especially for Pevatron search.
So it's actually kind of this multi-messenger work that is ongoing in astronomy, right? Actually, you were showing your presentation that we want to combine gamma rays observation and neutrino observation for this Pevatron. So I actually take already this question to ask you why we want to do that, why we want to combine these different messengers, what information we get.
Yeah, so for Pevatron, it will be extremely important, because what we are actually looking, we should say we are looking to cosmic ray sources. So what we are talking about Pevatrons, I'm talking about, which is say hadronic Pevatrons. It means Pevatrons that are accelerators of cosmic rays, of charged particles. And therefore, having also neutrino coming from a source, it would be actually extremely important, because neutrinos can only be produced by cosmic rays, while gammas can be produced both by cosmic rays but also by electrons. So having both information will be extremely important, because somehow neutrinos would pinpoint the source, but then we need gamma measurements, because we need to know the characteristics of the source, the morphology, how large it is, and these neutrino telescopes maybe will do it sometime, but at the moment it's not possible. So this for sure, having both detection would really somehow tackle the problem of galactic cosmic ray origin.
They combine each other. I like that.
Yeah.
So I have also a question for Judit. You were talking about these galaxy clusters, your source, and so as maybe the sources for dark matter, but you also mentioned that they are the biggest objects in the universe. So I was wondering, if you are looking to a galaxy cluster and you detect gamma rays, how do you know that they are coming from dark matter and not from other sources?
That's a very nice question, because indeed in galaxy clusters we do know that there are cosmic rays, right? So because of we have been able to detect them in other wavelengths. So what is really triggering a detection of dark matter is the energy spectra that we get from this detection, because it really looks nothing like anything that we are being able to detect until today. We expect dark matter to have a unique mass, which is expected for everywhere where is dark matter. All the dark matter has this characteristic. So this means that we cannot have a spectrum which goes above this dark matter mass. So if we find this dark matter signal, it has to be compatible everywhere where we get this signal, just not about the dark matter mass that we should expect.
So I guess this is related actually with the energy resolution of CTO, no? That's why we are waiting for CTO to be built. And
really, really nice because CTA is going to explore an energy range which we haven't been able to reach within the current telescopes that we have, neither in LHC with the colliders. So this is really a new window open for all this fundamental physics.
So thanks a lot. And I'm moving again to Anna. You mentioned something that it was very interesting to me. You were mentioned that in social media, in the accounts that you're working with, you've seen that you have a lot of women watching the content, but they are not interacting with the content. So considering that you are part of a lot of different international outreach committees, I would like to ask you, as big organizations, what can we do to increase the participation of women in our social media? How can we maybe make them feel comfortable to comment, to share, to...
That's not an easy question to answer to. It's I think it not only a problem of big organization, big scientific organization, but I think it's more of a social attitude that the women tend to have, and I hope the new generation will have less. That people tend to stay in the backstage and not be in the front. So they listen, they think for themselves, and they're less likely to share or to raise their hand. This sometimes is also because men tend not to listen to women, and so when you say something and you're not heard, and this is something that is common to many of us. You say something and then nothing happens, and after some time a man comes and say exactly the same thing, and after a while they say, has he have said? And because the voice of man is heard much more. This is something that is known, and I was hoping that in my lifetime was going to change, and this is not changing enough. We are working for that, of course, but so I think it's a more general attitude of being respectful of everyone and not caring about their gender if they say something, and making them sit, and starting with young children, not to teach them to be polite and behave when they're women, when female, and run and be whatever when they're men. So I think that it's a larger issue, but we can make something just working with them and showing that we are that it is possible. And if you are not feel completely comfortable, nothing happens if you go out and say something.
So it's part also of all these activities in education, or what we mentioned a couple of times in this event, that at the end we need to start in the youngest, with the youngest. So we really change things in a not medium, but long term even.
Yeah.
Okay, so thanks a lot. I move also, sorry, I have a lot of questions for you today because I love your presentations. So I have a question for Heide. At some point you showed that actually we have like 12 candidates for Pevatrons, only one, it was confirmed. And so somebody coming from outside the gamma ray astronomy would find this very strange. I mean, if we compare it to optical astronomy, for example, in which we have catalogs with thousands of sources, this is a really big difference, no? So it's kind of two questions. From one side, why is this happening in gamma ray astronomy? Why don't we have already these catalogs, these super big catalogs? And then what information we could, or what information we are missing, or what information can we obtain once we start confirming these candidates?
Yeah, so the reason I would say that first of all is that high energy gamma astronomy is relatively actually also a young science. I mean, it's not optical telescopes were there since much more time. But one of the reasons is also is that we are looking at the most extreme energy of the photons. And if you consider sources, how the flux of the sources decreases with energy, this is going down often like power law, so very, very steep. So this means that to detect them, you actually need a large surface. So you need to have a larger detector. So you need to have that to see these sources. And so what has been started to do, I mean, now we look at lower energies. So what has been already done by the present generation Cherenkov telescope, like HESS, MAGIC, and Veritas, they have actually seen, there started to be hundreds of these. So we start to have catalogs and to have real information. But if you were asking especially about these 12, so there, what really has started somehow last year was somehow a new window has been opened on the universe, because we are looking at extremely high, ultra high energy gamma rays. So we're talking about gamma rays of 100 TeV and even 1 PeV, so 1,000 TeV. This has never been seen before. So this somehow really opens, and each time if that you are looking at a new region of the electromagnetic spectrum, you're actually seeing new things, how as it is happened when we're looking at the radio telescopes, or we're looking at X-rays with gamma rays, and now we're looking at extremely, so ultra high energy gamma rays. So I think this is really very, very exciting, and what will probably, I mean, this first hint of these pevatrons has started since these new detectors came. But what we said is that it's probably not enough. We have to put together information, because we can look at high, but we also have to understand how these, how were possible to accelerate cosmic rays or electrons to so high energy to produce this extremely ultra high energy gamma rays. So it will come. I mean, in the next years, I think we really have, we really will start this new kind of ultra high energy gamma ray astronomy.
Yeah, it's very exciting, no? As you mentioned, like opening a new window of the electromagnetic spectrum at the end. It's also what we do not expect to detect, no? Like the unforeseen so far. So let's see what we can detect in the upcoming years. So thanks a lot. And I'm moving to Judit, because Judit, at the end you mentioned a very nice and inspiring words to next generations. But I actually want to ask you if you have a role model that inspire you and that actually let you to decide going to this high energy astronomy career.
Okay, that's a pretty difficult question, because as I was saying before, I didn't know really any woman physicist in science, because they are not in textbooks, right? But however, I had the really good opportunity to have a woman teaching me maths and physics and chemics during the high school. And for me, that was the key to everything, because I was able to see that I was not the only one that was loving math, that was curious about everything, and that wanted to know more about the universe that I'm living. So then, when I entered the career of physics, of course, I had more women teachers, and I see them doing very different things in physics, like from theoretical physics to astrophysics to applied physics. And then it's when I realized that it hasn't need to be a very big woman that has made like a very strong development for physics. Like, for example, Marie Curie. We all know and love Marie Curie, but really the science that we are making is made by the women that are in our institutions, in our universities, and these women are also role models for us, because are the ones that are closest to us.
I love that, the women that are actually working on a daily basis behind the scenes. Okay, so I think we are going to close here the event. I would like to thank you again for joining us today and share your knowledge and your experience. I would like you to finish actually the event maybe with one sentence that you would say to the next generation of women in science. So maybe we can follow the same order as the speakers. So Anna, if you start saying something to the next generations.
Just be yourself and conquer the world.
Love that. Heide?
I think if you have the will and an objective, you just have to go on, and it will be maybe hard, but you still have to go on. This is the most important thing, the will to do things.
The hard working. And Judith?
That if you are curious and you like to know more about the things, don't be afraid of asking. Ask as much as you want until you get an answer that really fits you. And this will make you understand the things you want in life, however the field it is.
So thanks a lot for this inspiring sentence for the future generations. And thanks again for joining us today in Women CTA. And thanks to all the audience that joined us today. And don't forget to follow CTAO in all the social media so you stay tuned to our upcoming events. And see you next year in the 5th edition of the Women of CTA. Thanks a lot, everybody. Ciao, ciao.
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 Ciao.